Hey everybody, welcome back to another lecture video. In this chapter and in this week we are going over chapter 14, and we are going to look at alcohols, we're going to look at ethers, and we're going to look at thiols. We'll probably focus the majority of the time on alcohols, and then we'll look at how ethers and thiols are similar, and then moving forward, even if we cover some reactions of ethers and thiols, it's the reactions of the alcohols that we're going to take with us. All right, so let's start with alcohols. Now, alcohols are compounds that contain an OH or hydroxyl, a hydroxyl group, and these are bonded to a tetrahedral carbon. So, a carbon that either has, a carbon that has 4 bonds. So they're organic compounds, right? Because they're bonded to carbons. Methanol, for example, would be the simplest. CH3OH. And that OH there is what makes it a alcohol. Now, as far as nomenclature goes, we will select the longest carbon chain that contains the OH, and that will be part of the parent alkane. We'll number it from the end that gives the OH the lowest number. We'll change the ending of the A and E of the alkanes into well, I guess it's really the E that changes to OL. So if it's hexane, it becomes hexanol. So the E becomes an OL. And we use a number to show the location of the OH. We'll name and number substituents and list them in alphabetical order, just like normal. So you're going to bring in some. So we've got some examples here, and we're going to do some naming examples too. So just to show you some of the simplest. So we looked at methanol already. So here's a 2-carbon ethanol, 3-carbon propanol, and notice that with our propanol, we can have the OH either attached on the ends to give a 1-propanol, or it can be attached in the middle, on the middle carbon, to give a 2-propanol. And of course, as groups, we would call this, well, actually, we wouldn't call this as a group. These are common names. So ethyl alcohol is a common name for ethanol, propyl alcohol, or isopropyl alcohol. Sometimes we just say isopropanol. That's kind of a common name as well. And that's rubbing alcohol, if you didn't know. And then we have 4-carbon. And for 4 carbons, you can see that there's a few places we can put the OH. It can happen here on the end. It can happen on the second of our straight chain. We wouldn't go and show it on here because that would just be the second carbon going this way. But we know that from looking at butane, there's a few different butane isomers, right? So here is a 3-carbon in a row chain with a branch, and then it's on one of those ends to give 2-methyl-1-propanol. We can also stick the OH on the middle of this little grouping, as shown here, 2-methyl-2-propanol, or tert-butanol, and we can go into why that's tert-butanol and why this is sec-butanol in a minute. And then for our cyclic compounds, you can see we would just change this from cyclohexane to be cyclohexanol. Cyclohexyl alcohol would be the common name there. Now the tert comes from tertiary alcohol and secondary alcohol. A secondary alcohol is an alcohol that's connected to a carbon atom that has 2 other carbon atoms on it. So if you look at sec-butanol, this carbon atom here that the OH is on is connected to 2 other carbon atoms. And likewise in tert-butanol, the OH that carbon that OH is connected to has 3 carbons attached to it, making it a tertiary alcohol. So a primary alcohol would be a carbon that only has 1 other carbon attached to it. And a good example here would be 1-propanol. Oops, that wasn't exactly what I wanted to do. So the carbon that the OH is attached to is attached to one other carbon. So that would be a primary. We'll show you this in a formal slide here in a second. Let's try naming. So pause the video, give these a shot, and then I'm going to name them. So pause the video, give these a shot. All right, here come the names. 4-methyl 2-pentanol. I guess I should work out the naming in front of you rather than just naming it, huh? Okay. 1, 2, 3, 4, 5. So it's pentanol, but it's 2-pentanol because that's where the OH is. 2-pentanol with a group that happens on the 4 carbon. So it's a methyl group on the number 4, so we say 4-methyl 2-pentanol. B, automatically that's the number 1, and this is the number 2, because I can name a number from wherever I want and go in whatever direction I want, and since it's an alcohol, let's just make the alcohol the number 1. So this is a methyl group on what looks like a cyclohexane alcohol. So I'm going to say 2-methyl cyclohexanol. Now, there's one other thing going on here that we have to address. When there's 2 groups on a ring, remember, not a benzene. In a benzene ring, they all stick out in the same direction. But on a flat ring, or not on a flat ring, but on a cyclic ring like this, remember they have axial and equatorial positions, but also they can be on opposite sides of the ring as each other. So, in the case where they're on opposite sides here, illustrated by the dashed and solid wedges, this would be trans. So I'll forgive you for not remembering this is trans part. 2-methyl cyclohexanol, though, would be the big name. 1, 2, 3, 4, 5, 6, 7. So this is heptanol, and it's 2-heptanol. And last but not least, so this looks like we've got a 1, 2, 3, no matter which way we go. So this is some kind of propanol. Because we know that there's multiple types of propanol, different places we could put the hydroxyl. This has to be labeled as 1-propanol. And then we see that there are not 1 but 2 methyl substituents, so we can say 2,2-dimethyl 1-propanol. All right, so as far as the IUPAC system goes, which is the international standard that we've been using, compounds that contain 2 hydroxyl groups are named as a diol. 2 OHs, and so you can see here ethane with 2 OHs, so this is ethane diol instead of just ethanol. Here they're not on the same carbon. Well, even if they were, we would have to say 1,2 ethane diol or 1,1 ethane diol. Whenever there's multiple groups, you have to name where they are. Here you can see there are 3 hydroxyls on this propane molecule, so this is propane triol, and it's 1,2,3 propane triol. So yeah, if there are diols and triols, and they keep the name of the parent chain, and we just say diol or triol after it. So hexane, triol, and so on. We commonly refer to compounds containing 2 hydroxyl groups that are next to each other as glycols. So that's just a term. So whenever you hear glycols, this means you've got an organic compound that has at least 2 hydroxyls next to each other. All right, let's talk about physical properties. This is showing you that alcohols are polar molecules. So the carbon-oxygen bond and the carbon-oxygen bond is here, and the oxygen-hydrogen bond here are both polar covalent. So this goes back to oxygen being electronegative, or more electronegative than the other two. And so electrons are being pulled in those directions in these bonds. You can see the area of electron density in red here and areas of electron deficiency in blue. So it's easier for the oxygen to pull electrons away from the hydrogen atom, but not so much from the carbon atom. So the carbon still retains some of that electron density, but both of them effectively get little positive charges on them. Okay, little positive charges, and yeah, that makes these polar. So alcohols are polar. Now, in addition to them having these bonds and being polar, there's also hydrogen bonding that takes place. So in the liquid state, alcohols associate by hydrogen bonding with each other. So you got to remember there are lone pair electrons hanging out on top of these oxygens already, as well as the negative charge. These lone pair electrons can participate in hydrogen bonding. So what you're seeing here is electrons reaching out and sort of making a bond, a pretty strong one. It's more of a ionic attraction to the positively charged hydrogen of a neighboring alcohol. And likewise, that same alcohol that's doing this has a hydrogen itself that can be hydrogen bonded to. And on top of that, these oxygens have the ability to hydrogen bond more than once. Three times, right? They can donate their electrons in 2 hydrogen bonds, but they also have a hydrogen that can receive electrons in 1 bond. So this gives alcohols higher boiling points than we've seen so far in the organic molecules. This little interaction here is what makes these molecules very sticky with each other. So just to give you a comparison between alcohols and their essentially equivalent mass alkane in a few categories. So boiling point, so we can see how this hydrogen bonding really affects the polarity and the hydrogen bonding, because these are also the first molecules that we've really seen some polarity to. We have seen alkanes and alkenes and alkynes, but these didn't have very many functional groups that were polar on them. So what you can see here is compared between methanol and ethane. Negative 89 was the original boiling point of ethane, and now methanol, which even has 1 less carbon on it, is 65 degrees. So very, very big change, almost a 100-degree change. And you see that for all of them, between propane and ethanol, between butane and 1-propanol, between pentane and 1-butanol. So just like the alkanes increasing in their boiling point as their chains got longer, alcohols will follow that same trend, but just comparing them to the same kind of molar weight alkane, they are way higher boiling point. And then as far as solubility goes, this has to do, going back to, to this feature, the polarness, right? Water really likes alcohols because water also has hydrogens that will participate in hydrogen bonding. And it can do it 4 times. So water is going to be really good. This isn't the molecule that one's hydrogen bonding to, but water really likes to dissolve things that are either charged or partially charged, and that means polar. So where methanol is soluble, ethane is not soluble. In fact, all the way through 5 carbons, we know that our alkanes are basically insoluble. And you can see here that's mostly true until we start getting into the larger alcohols. Again, to have a higher weight alcohol, higher weight molecule dissolved, we need to have more polar groups on it. So maybe a diol or a triol of this type would be more soluble. But you can see the solubility is already dropping off a little bit. 8 grams per 100 grams of water versus infinite. So, yeah. Big difference just by adding that functional group. Let's talk about the acidity of alcohols. So alcohols have about the same pKa value as water. Let's say same pKa value. And I think I mentioned this a little earlier in the last chapter when we were looking at benzene, its derivatives, phenol. Yeah, alcohols are going to be able to lose their H's just like water can, but they're not going to be comfortable that way. So we would typically wouldn't consider alcohols to be acids. Now, alcohols and phenols both contain OH groups, but phenols are weak acids and they react with sodium hydroxide. And alcohols don't do that. They're much weaker than phenols, so they don't even react with sodium hydroxide in the same manner. So while this happens, this won't happen. I guess it would be C minus and H2O and Na plus. That does not happen. Oh wait, my bad. There's an O here. CO minus. So this does not form. No forming. Only acidic alcohol is phenol. We can look at some of the effects of dehydration. So elimination of a water molecule from a alcohol gives a alkene. So alcohols minus water, alkene. So we saw in the alkene chapter that we could hydrate a double bond with a hydration reaction, and that put a water molecule in it, an H and an OH, right? H and an OH. It added that to both carbons of the double bond. This creates alcohols. So we can undo this. Now, dehydration is most often brought about by heating an alcohol with either 85% phosphoric acid or concentrated sulfuric acid. So as is H2SO4. There's a catalyst involved, some kind of acid catalyst. Now, primary alcohols are the most difficult to dehydrate, and they require the highest temperatures. So for primary alcohols, it's about 180 degrees Celsius to get these to dehydrate. Secondary alcohols are somewhat easier, lower temperatures. They undergo acid catalyzed dehydration at lower temperatures. I don't have an actual temperature to tell you, just know that 180 is a lot. And tertiary alcohols, these will actually work at just about room temperature. So let me say room temp, and this is not this hot. So yeah, it's a lot easier to get a tertiary alcohol to undergo a dehydration. So let's take a look at what we've got here. So ethanol here is a primary alcohol because it's attached to a carbon that only has one other carbon. So you have to picture, it might be easier if you guys draw these out. That the water molecule is going to leave from the two carbons. So an OH and an H from each carbon will take off. Obviously, it can't be from the same carbon, and maybe it's not obvious, but this is the case. We cannot lose an H and an OH from the same carbon, okay? So don't do that. And then in place of these two, the double bond will reform. Now, in the event that the OH that you pull off has choices between which hydrogen it can take from a neighboring carbon, there is going to be a sort of anti-Markovnikov rule, and we'll look at that. Cyclohexanol is a secondary. This carbon right here is attached to two others. So about 140 degrees here, so not as hot as 180. And again, here there's choices, but they're symmetrical choices. There's H's and H's on both of these, so it doesn't matter what direction this happens in. Even if it happened this way and we have the double bond up, realize that this just rotates a little bit and it's the same as this one. Water molecule. Always got to show the water molecule. When isomeric alkanes are obtained, the alkane that's having the greatest number of alkyl groups on the double bond usually predominates. So this is another way of saying it's going to remove it's going to try to keep all the hydrogens together. I don't know if that's the best way of saying it. Let me kind of show you what I mean. So here we have a choice. We're attached to this carbon. This carbon has this carbon on it, CH3, and then it also has CH2CH3. Now, it could form two ways. It could form here, and we get this double bond in between the two carbons. So what I mean is one of these H's here gets removed with this OH. Or we could get here, between these two carbons, in which case we're going to get a double bond here. Now, in this case, I don't think it matters so much. I'm trying to see what if I can explain it to you in an easier way. It's going to pull hydrogens off of the side that has less hydrogens on it, if that makes sense. So this side over here had 3 hydrogens to pick from. This side had 2. So it's going to pull from the side most often from the side that has less hydrogens. That's kind of like when we said the hydroxyl, when it's adding, will go to the side that has less hydrogens. So it's kind of the same. Hydration and dehydration, the hydroxyl or the double bond is going to go to the carbon that has least hydrogens on it. So that's why this one is the major product and this one is the minor product. Let's see it down in this bottom example. So here we have a carbon that has 2 choices. Again, there's this choice that has 3 hydrogens on it, and then there's this choice that only has 1 hydrogen on it. And so the double bond, majority of the time, is going to form there to that carbon. Now, it will still also form the other case, and I told you guys before, these are never 100% reactions. There's always going to be, well, not whenever there's multiple products, there's not always going to be 100% of one. There's going to be a mix. Now, there are some reactions that don't have side products, but that's not what I'm talking about. Okay. So if you were showing this reaction, let me think of a nice combined problem. You could potentially start with 2-butanol. I could ask you to dehydrate it and tell me the name of the 2 alkenes that it could make. So since there are 2 choices, you would draw them both. You don't have to know which is major, which is minor, unless that was the question. But in this example of what a question could be, it's about naming. So you'd have to be able to name 2-butene and 1-butene. Okay, dehydration and hydration are in equilibrium with each other. Acid-catalyzed hydration of alkenes to give alcohols, and acid-catalyzed dehydration of alcohols to give alkenes are competing reactions. They're happening in both directions. That's what the 2 arrows here are showing. The hydration is happening, but also the dehydration is happening. And so there is an equilibrium there, and that's what these 2 backwards arrows mean. In accordance with Le Chatelier's principle, which is affecting equilibrium or about systems in equilibrium, if we stress the system, if we try to shift it to one side or the other, it will reestablish equilibrium. So where large amounts of water, if we add that at the beginning of the reaction, that's actually going to favor the alcohol formation. Whereas removing the water from the equilibrium mixture is going to favor the alkene formation. So if I wanted to make an alkene and keep an alkene, if I wanted to make an alcohol and not have any alkenes at the end, I would just add lots and lots of water. Even as the reaction is half over, I'd add more water. And that's going to keep driving it forward. If I am wanting the alkene, then I'm going to probably be starting with an alcohol and trying to dehydrate it. So in that case, I'm going to add something to my solution or add something that's going to be scooping up this water to remove it. So as each alcohol molecule dehydrates and a water forms, something is going to go and scoop it out and take it, or pull it out of circulation so that the reaction keeps going this way, so there's no water to add to the backwards reaction. So that makes creation of alkene from alcohols and the alcohols from alkenes a pretty easy and efficient chemical reaction. Let's talk about oxidation of alcohols. Oxidation of a primary alcohol will give an aldehyde or a carboxylic acid, depending on experimental conditions. So if we use, let's say, what is this guy called? This is potassium dichromate. If we use potassium dichromate on a carboxylic acid, I'm sorry, if we use potassium dichromate on 1-octanol on this alcohol, the first round of oxidation is actually going to create the aldehyde. Now, if we allow this to continue to react, if we don't stop it or we just try to push it all the way to the end, then we'll get the carboxylic acid. And notice what's changing here. So we have a carbon that has a hydrogen, and an OH. And oxidation means that we're increasing the bonds to O while decreasing the bonds to H. So what we end up with is a carbon now double bonded to an O and only one H. So it still has 4 bonds. There's 4 bonds, but we've increased the bonding to O while decreased the bonding to H. And then additionally, it happens again. So still has 4 bonds, but now 2 bonds to O, well, technically 3 bonds to O, where it only had 1 and 2 before. That's what oxidation is in this context. So alcohols get oxidized into aldehydes, they get oxidized into carboxylic acids. And these only happen for primary alcohols because the alcohol has to be, the OH group has to be on the end carbon. If it's on the middle carbon, then it can't lose 2 hydrogens because it doesn't have 2 hydrogens. It only has 1. Notice that this carbon, this alcohol, started with 2 hydrogens on it, and now it has none. If I was to show you this same, if let's say this was 2-octanol, so 2, 3, 4, 5, 6, 7, 8. So 2-octanol is this. This only has 1 H on it. That carbon only has 1 other H, and then it has 2 other carbons on it. So we could do this and make this into a double bond to an O and lose the H altogether, which is what happened in the first step here. But we wouldn't get an aldehyde, we'd get a ketone. So you're going to see in a second that secondary alcohols give us ketones, while primary alcohols give us aldehydes. And this is only because of the limitation on hydrogens. There's no more hydrogens to pull off and no more places to stick O's on to get a ketone to oxidize any further. So here is another example of a ketone. So again, this carbon right here that the OH is attached to only has an H on it. And so in this reaction, this oxidation reaction, that H is being removed. That bond forms a double bond with the hydrogen. And yeah, we get a ketone. Let's see. I know we're gonna go over nomenclature for these guys in a. Oh wait, aldehydes and ketones. For a second there, I thought, why haven't I told you how to name those? We're not in that chapter yet, so don't worry about naming the aldehydes and ketones. Just know that it happens. Now, tertiary alcohols. Tertiary alcohols, as you can see by that carbon having 4 bonds already, don't have an H on them, so there's nothing to remove, nothing to oxidize. These don't react. So tertiary alcohols do not react any further. Let's talk about ethers. The functional group of an ether is an oxygen atom bonded to 2 carbon atoms. So oxygen bonded to 2 carbons. Now, the simplest ether is shown here, dimethyl ether. So a 1 carbon and 1 carbon group on either side. And the most common ether is actually diethyl ether. So simplest and most common. Diethyl ether is so common that we just call it ether. This is the stuff that I think it was Albert Einstein used to walk around with a ether-soaked rag in his jacket pocket, and he would just pull it out and huff it. Unless I'm confusing Albert Einstein with every other scientist. I think it was Thomas Edison and who else? Niels Bohr. I think all of these guys used to huff ether. If you've ever huffed ether, you'll know why they liked huffing ether. All right. That was a joke. Don't huff ether. This is me having notification silencer and no. Oh, never mind. I was like, well, my notifications are coming and I have airplane mode on. Nope, didn't have airplane mode on. I apologize for this disruption. Okay, let's talk about the nomenclature for ethers. So although ethers can be named according to the IUPAC system, chemists always, for whatever reason, bring up common names for low molecular weight ethers. So for the ethers that are really low weight, we can use a common name. Common names are easy, and you don't have to know them. You can figure them out. They're derived from listing the alkyl groups bonded to the oxygen in alphabetical order and saying ether. So for example, here we have an ethyl and an ethyl. I know this is the one that I already showed you, but the common name for this is diethyl ether because there's two ethyls and it's an ether. In this case, we have a methyl and we have a cyclohexyl. Cyclo comes before methyl, so cyclohexyl methyl ether. Now, IUPAC names, we take the longest parent chain. In this case, it doesn't matter which one we take, it's ethane. And then we take the other part that's attached to the O and we say it's some kind of alkoxy. So methoxy, ethoxy, propoxy, butoxy. The name of the alkane plus oxy. In this case, it's ethyl, so it's ethoxy. So this is ethoxyethane. This is methoxy cyclohexane. See, they're naming this as the methoxy and just saying that is attached to a cyclohexane. That's the other way, the IUPAC name of naming ethers. We have cyclic ethers. Cyclic ethers are ones which the atoms obviously form a ring, and one of the members of the ring is oxygen. So cyclic ethers are known by their common names as well. Ethylene oxide is an important building block for organic chemical industry. It's used in like fumigant in foodstuffs and in textiles and in hospitals to sterilize surgical equipment. Tetrahydrofuran is a useful laboratory and industrial solvent as well, THF. Just examples, you don't have to know anything more about cyclic ethers. Let's talk a little bit about the physical properties of ethers. Ethers are polar compounds because they have that oxygen that has that partial negative charge, and it's bonded to a carbon that has a partial positive charge due to those electronegativities. However, only weak forces of attraction exist between ether molecules in pure liquids. So they're not like alcohols. They don't have that hydrogen bonding ability. They don't have any hydrogens on the O's, so they don't have that extra like pulling force on each other. But they are slightly polar. So because they don't have that large extra attraction that hydrogen bond brings, then consequently the boiling points of ethers are actually close to those of the hydrocarbons of similar molecular weight. They pack together almost slightly a little bit better than a regular hydrocarbon would. Ethers have lower boiling points though than alcohols of the same molecular formula. So these two are constitutional isomers. They're both the same formula. One's an ether, one's an alcohol, but you can see here marked difference in boiling point. Dimethyl ether's boiling point is much more similar to just this would look like propane. I don't know what I was trying to draw. I guess this was the hydrogen, this was the carbon, this is the other carbon, this is the other carbon, this is one hydrogen of the three for whatever reason. So propane and dimethyl ether would have similar boiling points. I think propane's was a little lower though than -24. Reactions of ethers resemble hydrocarbons in their resistance to chemical reactions. So hydrocarbons, with the exception of alkenes and alkynes, didn't react. So these ethers don't react with oxidizing agents like potassium dichromate. They don't react with reducing agents like H2 in the presence of like nickel or palladium or platinum. They're not affected by most acids or bases at moderate or high temperatures. So not reactive like alkanes. And because of their general inertness and good solvent properties, ethers like diethyl ether and THF are actually excellent solvents to carry out organic reactions in because they don't side react. Let's talk about thiols. Thiols, they're compounds that contain what we call a sulfhydryl group, an SH. Sulfhydryl group. Most outstanding property of low molecular weight thiols is their stench. Does that come across as like stinky? They're responsible for the smells from rotten eggs, from sewage. The scent of skunks is due primarily to actually these two thiols in particular, 2-butene-1-thiol and 3-methyl-1-butane thiol. Yeah, this is skunk right here. Yeah, so thiols. I think we actually add a thiol to natural gas. So when you can smell a gas leak, it's because it's got an added thiol in there for protection. That's how we know when there's gas leaks. Natural gas doesn't have a smell. IUPAC names are derived from the same manner as alcohols. So to show that this compound's a thiol, the final E of the parent chain gets changed to be thiol. So ethane thiol. I guess that's a common name. Why it should be ethanthiol? No, that doesn't make any sense. The E doesn't get dropped. Obviously, the E doesn't get dropped. The E stays. So it's not like the alcohols. So we keep the E. Ethane thiol, propane thiol. We just add thiol to the end. Now, common names for simple thiols come from naming the alkyl group and then adding the word mercaptan. So this is ethyl mercaptan because it's an ethyl, and then mercaptan here means thiol. Isobutyl, because of the way this is set up, right? Isobutyl mercaptan. But otherwise, we would just name this as a normal. So I could probably give you an example. Let's grab a thiol from your book or something and name it. Let's see. Your book has thiols in it, yeah? Here we go. So the one that I'm looking at is actually just this one backwards, so we won't name that one. We'll just do these two. I think that's easy peasy, and then let's just do that. Okay, so first one, this is cyclohexane. So this is cyclohexane thiol. Cyclohexane thiol. If this was if this is what we had, then this would be 2-chloro-cyclohexane thiol, because we're still going to call the thiol the number 1 no matter what, because it's part of the parent name. In this case over here, we've got 1, 2, 3, 4. So this is butane. So this is butane thiol. These seem too easy, huh? Yeah, the book doesn't have harder ones, so I think that's it. Obviously, we could stick. Oh yeah, let's try that. Let's stick. Let's go. Doot 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 doot, like that. All right. So this is 1, 2, 3, 4, 5. So this is pentane, pentane thiol, but we have to say where it is because this is on the 3 carbon. So this is 3 pentane thiol. Yep, 3 pentane thiol. I hope those were sufficient examples. Let's talk about the physical properties of thiols, mainly how they compare to alcohols and alkanes. Because of the small difference in electronegativity between sulfur and hydrogen, sulfur is actually 2.5, hydrogen is 2.1. It's about 0.4. So this is really just like carbon. Carbon is also 2.5, 0.4. So we call a carbon-hydrogen bond nonpolar, while a sulfur-hydrogen bond is just as nonpolar. And by these numbers, a carbon-sulfur bond is essentially pure covalent, perfect sharing. So that makes these less polar than alcohols, and as such, their boiling points are not going to be as high. They do have a little bit of hydrogen bonding, though, a tiny, tiny bit, but not a lot. Sulfurs also have a lone pair on top of them. Sulfurs also like to participate in 2 bonds, and well, they can also have more though because they have more electrons and more available shells. But these guys aren't going to contribute very much to the boiling point. So they have lower boiling points and are less soluble in water than other polar solvents than alcohols. So less polar means less soluble. In water, less soluble in water, and being less polar and having less H bonds means lower boiling point. And you can see that boiling point is 6 compared to 65 for methane, for CH3SH versus CH3OH. So there you go. Now thiols are weak acids and are comparable in strength to phenols. So thiols, like phenols, can lose their H to increase the acidity of water a little bit, but they can also react with sodium hydroxide, which is something that. So just to be clear, an acid like HCl, or even a weak acid here, I'm gonna use the notation for weak acid. HA. HA can dissociate into H plus and A minus. That's being an acid. So we're saying that phenol and thiols can do this. Phenol can lose an H, thiol can lose an H in water and become acidic. They can also react with sodium hydroxide. HA plus NaOH makes water and Na, a salt. So that's what we're seeing here. This ethane thiol is going to react with sodium hydroxide. This H and this OH are going to form a water. This is called acid-base chemistry. Acid bases, right? Not all acids not all molecules react with bases. Only acids do. Acids can do 2 things though. They can react with bases, and they can also just be acids and be ionized in water. So in the context of phenol, that meant that phenol was soluble where normally benzene molecules were not soluble, because phenol ended up getting a charge on it by doing this, right? This is phenol in the example. That's phenol, A minus. Water likes that. Water likes things that have charges on them. So for phenol, it meant because it was acidic that it could dissolve better. Thiols, we already saw, don't dissolve as good in water as alcohols do because they lack the hydrogen bonding ability. Now, they might be able to recover some of that solubility by the fact that they are acids. These guys can form, and they can become charged. They form slight ions. Now, pK of 10 means that this happens as often as it does with phenol. So we could say if phenol is slightly more soluble than a normal benzene, well then let's say Pentane thiol is going to be slightly more soluble than regular pentane, even though it's not going to be as soluble as pentanol, okay? And that's just because that alcohol with the hydrogen bonding really lifts up its ability to interact with water. Okay, and then they react with bases. So we get this as well. I was saying the water and a salt. Here's the water and here's the salt. So here's the acid and here's the base in the example. Thiols can also oxidize. The most common reaction of thiols in biological systems is their oxidation to disulfides. You may have heard of the disulfide bond. We usually refer to it as SS. Disulfide bonds take place between the cysteine residues in amino acids or in proteins. The amino acid cysteine contains a thiol, and this is partly responsible for the curly hair. If you have curly hair or if you have used chemical straightener, it goes and breaks the disulfide bonds. The disulfide bonds are what makes your hair curly. Thiols are readily oxidized to disulfides by oxygen. So you can see that here. Let's say oxidation by oxygen even. There are other oxidizing and reducing agents, but O2 and a thiol, you'll get a disulfide. They are so susceptible actually to oxidation that they must be protected from contact with air during storage. So these will readily oxidize. And disulfides in turn are easily reduced to thiols by several reducing agents, including hydrogen gas in the presence of a transition metal. So just like we saw earlier with reduction of unsaturated alkanes from alkenes or alkynes back into alkanes, that this usually takes place in a nickel, platinum, or palladium catalyst and hydrogen gas. Let's talk about some important alcohols before I let you guys go. Coal or methane, right? We can take coal or methane, we can oxidize it into carbon monoxide. We react it with hydrogen gas to make methanol. From methanol, we can make acetic acid, we can make formaldehyde. These are important. Acetic acid is useful in all kinds of things. We use it in food, we use it in the lab. Formaldehyde, has its uses too for storing biological samples. These can be easily made. Now, another important alcohol can come from ethylene. If we take ethylene through various reactions, we can get ethanol, which then can be made into diethyl ether, which we mentioned earlier is one of the most common ethers and an excellent solvent. It's an excellent organic solvent. And ethylene glycol. Ethylene glycol is antifreeze. Without antifreeze in your car, the liquid and the cooling components in your engine, to cool your engine, the water that moves around the radiator, all that stuff, that would freeze in the wintertime and it would boil away or be, you'd evaporate in the heat. But because we make ethylene glycol solutions and put that into your car, they have a much higher boiling point and a much lower freezing point than regular water would. So these are very important alcohols. There's one other or a few others that we can make. These are from propene. Propene is the raw material for the manufacture of these important glues. I'm trying to think of what resins I could name. I can't name any. Isopropanol or rubbing alcohol. Obviously, this is another really good alcohol for sterilizing, for cleaning, for wound care, for just, for cleaning electrical components. I clean my phone screen with isopropanol. Glycerin and glycerol. These are also good and useful. I can't think of what we use glycerol in food all the time. I think glycerin and glycerol are both used in food. You can probably think of other areas where these have come from. But again, alcohols, remember, we can make alcohols by hydration reactions, and we can make alkenes by dehydration reactions, and we can control them very easily with Le Chatelier's principle. So again, just to give you an overview of some of the more important alcohols. So again, isopropyl, glycerol, glycerin, formaldehyde, acetic acid. Some of these are maybe more important than others. All right, I think... I don't know why I'm zooming in on the screen like that. I guess that's it. So let me know if you guys have any questions. I'll be working on the Chapter 15 PowerPoint I'm sorry, the chapter 15 lecture. I think the PowerPoint is posted. And I'll see you guys in the next video. Take care, guys.